Okay, good morning all. So let me continue our discussion on orthonormal set. So let us start with any orthonormal set. Orthonormal set in a Hilbert space H. So we'll assume that the completeness of inner product space. So we have a Hilbert space H and EI is an orthonormal set. So this orthonormal set can be uncountable also. So but what we know is that we know that the set S we denoted as all those I in I such that let us take any vector x in H, and if we write the set S as all those I such that the inner product of x with EI is non-zero. So we know that this set S is at most countable. So now we would like to uh, give a meaning to the vector summation of x dot ei times ei. So to do that, notice that so this set is uncountable. So if S is empty set, then this, if we write summation of x ei I in I, so this is defined to be equal to just the zero vector, and if S is a finite set, if S is says just let's call that E1, E2, En, a finite set, then this sum is just the finite sum x dot ei I equal to 1 to n. And of course, this is just a finite sum, so it doesn't matter what order you take this E1, E2, En. But what happens if this is the countably infinite? Yes, is countably infinite. Let we can enumerate this set S as some E1, E2, and so on. So let E1, E2, En be an enumeration of S. Then we can talk about summation of x dot ei. So if we look at this partial sum. So then if we define yn equal to summation of x dot ei I equal to 1 to n, then what is norm of m bigger than n, norm of ym minus yn, this square if we write, this is summation of I equal to n plus 1 to m x dot ei norm square. And because these ei's are orthonormal, so this will be equal to summation of mod of x dot ei square I equal to n plus 1 to m. This is because this set ei is an orthonormal set. So therefore, also what we know is that by the Bessel's inequality, this summation of I in let's write I equal to 1 to infinity mod of x dot ei, this is square, this is finite, right? Because the Bessel's inequality says that this sum is less than equal to norm x square. So this is a convergent series. So therefore, this norm of ym minus yn square, this we wrote is equal to summation I equal to n plus 1 to m mod x ei square. This goes to 0 as n goes to infinity. Right? So this implies that this yn is a Cauchy sequence. This implies this sequence yn is a Cauchy sequence in H. So by completeness, we know that it must converge. So hence, and so it converges to some, let's call that y in H. So we are writing y is equal to summation of this this y is summation x dot ei I equal to 1 to infinity. So notice that this thing depends on the ordering of this set S, right? So if I take instead of this E1, E2, En, we take some other ordering, then we may get a different vector y. Again, whatever ordering we take, then this sum will converge to some vector, but it may be different. So what we would like to prove is that this is independent of the ordering. So claim is that this y is independent of the ordering C1 chosen. So to prove this, suppose we take some other ordering. So we write so this actually is not S. Yeah, here I wrote it wrongly. So our set S was just the index I for which this is non-zero. But here I am writing that same S. So this is I should write as something else. So yeah, if S is empty, then we write this, and this is S is equal to 1 to N, then we write like this. So, and if S is countably infinite, then we can write this set E so this is an enumeration of the set EI such that I belong to S. So we know that this is a countable set, so we can write this as E1, E2, En and so on, and then we do this. Now if we take some other ordering, so suppose E1 dash, E2 dash, En dash is another enumeration of the set E, then we can again take this sequence of partial sum, and we want to show that that will converge to the same y. So okay, one thing note is that in any Banach space, so what we know is that if a series is absolutely convergent, then it is independent of any rearrangement done, right? But here, if you see, if I look at summation of norm of this vector, then that is the summation of mod of x dot ei, which may not converge, right? So what we know only is that summation of mod of x dot ei square, this is convergent. So this can be convergent, but summation of mod x dot ei, it may be divergent. For example, this may be equal to 1 by I, and then this series convergent, but summation 1 by I, that diverges. So therefore, I mean, this series, they need not be absolutely convergent. So we cannot say using that result that this will be independent of the ordering. So what we have to use here is that this is an orthonormal set, and using that we can still show that for any rearrangement this series will converge to the same vector y. So if we take the sequence of partial sum, so let yn dash is equal to summation of x dot ei dash I equal to 1 to n, then as before, this is also a Cauchy sequence, and this will converge. So yn dash is a Cauchy sequence, and so it converges to some y dash belonging to h. So we want to show that this y dash is equal to y. So we need to show that y dash is equal to y. So let epsilon be any positive number. So we can choose capital N such that norm of yn minus y, this is less than epsilon, and norm of yn dash minus y dash is less than epsilon, and summation of x dot ei square is I equal to n plus 1 to infinity. This can be made less than epsilon square. This is true for all n bigger than equal to capital N. Because yn converges to y, yn dash converges to y dash, and this sum from 1 to infinity is finite, we can choose this capital N such that we can make these things arbitrarily small. So we made this less than epsilon. So now if we have any n bigger than equal to n, let's fix n bigger than equal to capital N, then we can find m bigger than equal to capital N such that E1, E2, En is contained inside E1 dash, E2 dash up to Em dash. So this can be done because this is just a finite subset of this E1 dash, E2 dash, and so on. This से निकाल दो. So we have uh, we can find M such that this happens. So now if we look at ym dash minus yn. So therefore, if we look at ym dash minus yn norm square, this will be less than equal to summation of x dot ei square I equal to n plus 1 to infinity, and this we know is less than epsilon square. So why is this true? Because we know that if we look at ym dash, then it is the sum from I equal to 1 to m of this x dot ei dash times ei dash, and because we have chosen this m such that this set contains e1 e2 en, so when you take this difference, then all those terms cancel, so only the thing will remain is the this where I is bigger than equal to n. So therefore this is less than equal to this sum, which we chose to be less than epsilon squared. So this implies that ym dash minus yn is less than epsilon squared. This norm is less than epsilon, and because this converges to y dash and this converges to y, we can show that y dash equal to y. So this will imply that norm of y dash minus y, if we take, this can be written as less than equal to we can write y minus yn plus yn minus ym dash and plus ym dash minus y dash, and norm of y minus yn is less than epsilon. Norm of yn minus ym dash by the above is less than epsilon, and ym dash minus y dash, that is again less than epsilon. So therefore we get that this is less than 3 epsilon, and this will imply that y dash equal to y. So what we see from this thing is that if we take any ordering of this set ei I belonging to S, then this sum, this infinite sum is independent of that ordering. So therefore we can define, so the conclusion is that we can define the summation of x dot ei I belonging to capital I unambiguously by choosing this E equal to sum E1 E2 En and defining this sum to be equal to the infinite sum and we know that this sum converges and it is independent of this chosen ordering. So therefore we can define this, though it looks like uncountable sum, but only countably many terms are non-zero, so we can define it like this. So this was just to show that one can define this sum for any orthonormal set. We can define this summation of x dot ei I in I, and this is a vector in H. So this is if we assume that it is a Hilbert space. And we also get this result that if we have any Hilbert space and ei is an orthonormal set, in H, then for any x in H, if we write x minus summation of x dot ei I in I, this is orthogonal to Ej for all j in I. So this we saw that this is true for if we take a finite or countable orthonormal set, but here now we can see that this is true. So here only thing is that by the previous remark we know that this sum is well defined, and then if we look at x minus this thing, then we can show this orthogonal to Ej by is simply writing this now as an infinite sum and then taking the inner product. So we have this thing is sum I equal to 1 to infinity of x dot ei, and then if we look at the inner product of x minus summation this inner product with Ej, then this will be equal to x dot Ej minus this sum. So this again I can write summation I equal to 1 to infinity x dot ei, and then we get ei dot ej, and then this ei dot ej is delta ij, so therefore this will be equal to x dot ej minus x dot ej, which is equal to 0. All right. So now we will define what we mean by a complete orthonormal set. Definition: an orthonormal set is said to be complete if it is a maximal. So if it is maximal with respect to the partial ordering on orthonormal sets induced by set inclusion. Right. So if we look at collection of all orthonormal sets and then define this partial ordering, that a set uh, S1 is less than equal to S2 if S1 is the subset of S2, and then if we get any maximal element with respect to this partial ordering, then we call that a complete orthonormal set. And any complete orthonormal set will be called an orthonormal basis. So a complete orthonormal set is called an orthonormal basis of H. So clearly one can see that by using Zorn's lemma, we can show that every Hilbert space has an orthonormal basis. So proof is simply you use the Zorn's lemma. So you have to only show that if you have any chain or totally ordered subset of this partial order set, then it has an upper bound. So if you take any chain, then the union is clearly an orthonormal set. So that will be an upper bound. And then by Zorn's lemma, it has maximal element. So the proof is simply follows easily using the Zorn's lemma. So now we will write the main theorem. Let H be a Hilbert space and let EI be an orthonormal set in H, then the following are equivalent. The first one is that this set is complete EI, I and I is complete. Second, if X is such that X dot EI, this is equal to 0 for all I in I, then X must be 0. So this is the same thing as saying that 0 is the only vector which is in the orthogonal complement of this set, right? So if something is orthogonal to all the vectors of this complete orthonormal set, so then this must be 0. Third statement is for any X, X can be written as summation of X dot EI. And the fourth one is if X is any vector in H, then norm of X square is equal to summation of mod X dot EI square, I belonging to I. This is the last one. This is called Parseval's identity. So in general, what we know is norm X square is bigger than equal to summation of X dot EI square. That is the Bessel's inequality. But here what we are saying is that if it is an orthonormal basis or it is a complete orthonormal set, then this norm X squared will be equal to this sum. So let's prove this theorem. So first we will show that 1 implies 2. So we are given a complete orthonormal set. Then we have to prove that if X dot EI is equal to 0 for all I, then X must be equal to 0. So we assume this set EI, I and I is an orthonormal basis. And X dot EI is equal to 0 for all I in I. We have to show that X is equal to 0. So if X is non-zero, then we have to somehow uh, contradict that this is a complete orthonormal set. So then if we look at this set EI, I in I and then we include this vector x by norm x. So what we know is that each vector here is a unit vector, and also oh, this is an orthogonal set because this I in I is already orthogonal, and if I take the inner product with x by norm x, then that is equal to 0 by this condition that x dot ei is 0 for all I. So this is an orthonormal set, and this is strictly bigger than this given orthonormal set. Right? So this is an orthonormal set. So that contradicts the maximality of this set. So which contradicts the maximality of EII in I. So therefore x must be equal to 0. Now we will show that statement 2 implies statement 3. So suppose we have any x in H, we have to show that x can be written as summation x dot EI. So let x be any vector in H, then we have written this proposition that x minus this vector is orthogonal to each ej, right? So we'll use this. So by the previous proposition, x minus summation I in I x dot ei is orthogonal to each ej j in I. But we know that by 2, if any vector is orthogonal to each vector in this set, then it has to be 0 vector. So this implies x minus summation xei this is equal to 0 by 2, and which implies x is equal to summation xei. So 2 implies 3 is done. Then we will prove 3 implies 4. So if x is equal to summation xei, then we have to show that norm x square is equal to summation of mod of x dot ei square. So to do this, we know that this summation x dot ei I in I, this is nothing but summation of I equal to 1 to infinity x dot ei, right? By choosing this set ei, set E equal to E1, E2, and so on. So this is equal to this sum, and therefore, if we look at this can also be written as the limit of n tending to infinity of yn, where yn is equal to summation of x dot ei I equal to 1 to n. So then we know that norm of yn square is nothing but summation mod x dot ei square I equal to 1 to n. Then by taking limit as n approaches infinity, we get norm of x square, because yn converges to x. Right, so this is equal to x, we know. So since yn converges to x, norm yn converges to norm x. So this will converge to norm x square, and the right hand side converges to summation I equal to 1 to infinity of mod x dot ei square, which is same thing as summation of I in I x dot ei square. So this shows 3 implies 4. Now we will be done by proving that 4 implies 1. So 4 says that this Parseval's identity is true. Then we have to show that the orthonormal set is complete. So if it is not complete, then what do we get? So assume norm x square is equal to summation mod x dot ei square I in I for every x in H. Then we have to show this ei I in I is complete. Suppose it is not complete, then there exists some vector, there exists some E in H such that this ei I in I union E, because if it is not complete, then there exists this is not a maximal orthonormal set, so there exists a bigger orthonormal set. So we have a vector E such that this is an orthonormal set. But this implies the that E with ei, this is equal to 0 for all I in I. But if this happens, then what is summation of I in I mod of E dot ei square? This is equal to 0. But we are assuming that this has to be equal to norm of x squared. So this is not equal to norm E square, because norm E is equal to 1. So this means that we don't have this Parsable's identity true for this vector E. So therefore, we must have that this is complete. So this theorem gives the following corollary. So let I in I be an orthonormal set in a Hilbert space H. Then this set is complete if and only if the subspace of all finite linear combinations of these vectors EI is dense in H. Right? So this completeness is equivalent to saying that if we look at the subspace of all finite linear combination, that is a dense subspace of H. So we have to prove if and only if. So one way is that if we have this is complete, uh, if this set EI is complete, then we know that X is equal to summation this X dot EI I equal to 1 to infinity, which is this limit of this finite sum X dot EI I equal to 1 to n. So this belongs to the subspace containing finite linear combinations, and its limit is X. So this implies that this subspace is dense in H. The subspace of all finite linear combinations of EIs is dense in H. The other way, suppose this is a dense subspace, then we want to show that EI is complete. So for that, we will show that if there is any vector which is orthogonal to all these EI, then it has to be 0. And then that was the statement 2, So that will imply that the set is complete. So let's assume that the subspace of all finite linear combinations of EIs is dense in H. Then if there is an element which is orthogonal to this subspace, then it has to be 0, right? So then if X belonging to H is orthogonal to this subspace, then X must be equal to 0, because we know that the orthogonal complement of any set is equal to orthogonal complement of its closure, and orthogonal complement of H is equal to 0, so X has to be 0. So this implies that if X is orthogonal to each EI, then it has to be 0. So this implies if X dot EI equal to 0 for all I in I, then X must be equal to 0. Because if this is true, then this X will be orthogonal to any finite linear combination of these EIs, and that will mean that X is orthogonal to all the vectors in this subspace, and that we know implies that X has to be 0. And then by 2 of the previous theorem, this implies that this set is complete. Okay, so I don't have time. The next theorem next time I'll do that. If we have any separable Hilbert space, then it will have a countable orthonormal basis, and the converse is also true. So a Hilbert space is separable if and only if it has a countable orthonormal basis. So that will do, and then maybe I'll give a few examples of orthonormal basis for some Hilbert space. So for L2, for example, little L2 and capital L2. So that we'll do in the next class.